All right, 4.2, day 2 is more on logarithmic functions. And so this part of the lesson, we're going to find the domain of a log function. We're going to use common logs, and we're going to use natural logs. And so in the last lesson, we looked at the graph of a log function. Remember, we had said that it was going to have a vertical asymptote at the x equals 0, and our graph was going to come up, and it was going to look like this. Now, it doesn't matter what the base is. This is the general shape, and they are all pass through that point, which is at 1, 0. The only time that they're not going to pass through the point 1, 0 is if our graph has been shifted up, down, left, or right. Even if there's a horizontal or vertical stretch or compression, it's still going to have that point at 1, 0. So here it talks about the domain, and so we can look at the graph and we can see that our graph does not keep going to the left, but it does go towards the 0. And remember, it's never going to touch it, but it's going to get really super close to it. So our domain is going to start at 0, but it does keep going to the right, therefore it goes to positive infinity. The range, our graph keeps going down, so from negative infinity, and it keeps going up to positive infinity. We already talked about that they're going to go through the point 1, 0. And because there is, which is your x-intercept, and because there's an asymptote there on that y-axis, that means there's going to be no y-intercept. Now, something we didn't talk about, because all the graphs we looked at the last lesson looked like the one above, but if our base is greater than 1, then our graph is going to be going up, and so it's going to look like the one that we drew above there. But if our base was a number between 0 and 1, our graph would be decreasing, and so it would be going down. It would still have that asymptote there. It would just come down. It would still go through that point 1, 0. It would just be going down instead of up. All right, and then we talked about that x equals 0 is that vertical asymptote. All right, so let's talk about the domain of a log function then. It says the domain of an exponential function of the form f of x equals b to the x includes all real numbers, and its range is a set of all positive real numbers. Because the log function reverses the domain and range of the exponential function, the domain of a log function of the form f of x equals log base b of x is a set of all positive real numbers. In general, the domain of f of x equals log base b of x consists of all x for which g of x would be greater than 0. All right, so what it's talking about there at the beginning is, remember in 4.1 we looked at exponential functions. And we had said there that they had their domain was negative infinity to infinity, and their range, they had that horizontal asymptote to 0, and they went up to infinity. Well, now we're looking at log functions, and we have said that our domain, we have that vertical asymptote at 0, and it keeps going to the right to infinity, and our range keeps going up and down, therefore it's negative infinity to infinity. And so what it's talking about is, remember, we've said that the exponentials and logarithms are inverses of each other, and so that means that their domain and range is going to switch, and we can see there that it did. Now, if I want to find the domain of a log function, all I have to do is take its x value, so whatever's right there, that x value, and we're going to set it greater than 0, and then we'll solve, and that will find us our domain of a log function. So let's do that. Example 1, it says find the domain of log base 4 of x minus 5. So we're going to take the x portion, which is our x minus 5. We know that's got to be greater than 0. And we're just going to solve. And so we get x is greater than 5. Now, if they want an interval notation, it's usually easier for us to go with the number line in between. So we know our graph is going to start at 5, and it's going to shade towards positive infinity. And so I can see my interval notation is from 5 to infinity. 5 is going to have a parenthesis because it's not equal to. All right, and in example 2, it wanted us to illustrate this, okay? So I want to use some transformations here. Now remember we said that, well, first thing, let's look at the function. It says we're looking for log base 4 of x minus 5. That x minus 5 is a horizontal shift right 5. And so remember, if we were doing our table, that means we would take all these x's and we would add 5 to them. Well, let's think about some things we know. For one thing, we know that all the parent functions, which this would be a parent function if it didn't have the minus 5 there, have a vertical asymptote at x equals 0. But we're moving ours to the right 5, so now it's going to be at x equals positive 5. They also go through the point 1, 0. here's your x value. We're going to move it to the right 5, so now we're going to have the point 60. So if I wanted to graph this, I still have that vertical asymptote. Let me change colors here. At, whoops, I'm sorry. We just showed that it had moved to 5. So 1, 2, 3, 4, 5. I believe that's 5. It's right here. Alright, we know it's going to have that point 60 now. My base is a number greater than 1, so it's going to be increasing. So it's going to look like all of our others did. And so we can see here that our domain, our whole graph, literally shifted to the right 5. Alright, then common logs. A logarithm function with a base of 10 is called your common log function. So f of x log base 10 of x is usually just expressed as f of x equals log of x. So when you see log of x, you know that's the same thing as log base 10 of x. Now be careful, because notice this x is the same size as the letters in the log, okay? The reason I'm pointing that out is because what if you had log of 10? This is the same size. That is your x value. Down here, the subscript would be your base. If there's not one written, like on this one, then we know by default it's going to be a base 10. Alright, so just be careful of that. And so we could work out problems just like what we did in day 1 lesson. We could say we have log of 10 equals x. And so we know our base, right here, that base would be 10. Our x is 10, and our y is now an x. So we do our b to the y equals our x. And then remember, that's a 1. Bases are the same, so we know x equals 1. And don't let it confuse you if they put an exponent there, okay? If they put like a 3 there, then that would make our x3, would make this 3, and it would change our answer to be x equals 3 instead, okay? Still, look at how big that 10 is. Is it the same size as the O and the G, or is it written down below? Be careful of that. Alright, example 3 here says the percentage of adult height attained by a boy who is x years old can be modeled by that function there, where x represents the boy's age from 5 to 15 and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So they gave us this equation. Alright, make sure you know what your variables are. This is f of x. F of x represents the percentage of the adult height. So I'm just going to label it percentage height. X represents the boy's age. Now, read the question. Approximately what percentage, so we're after f of x, it's age 10. So we're going to let our x be 10. So we're going to type in 29 plus 48.8 log of 10 plus 1. Now notice this time they have the plus 1 in parentheses with the 10, which means you want to keep it in parentheses. If they didn't, we would have to make sure to close the parentheses after we plugged in our 10 there. Alright, so we're going to go to our calculator. We're going to type in 29 plus 48.8. Log is the button that's right there next to the 7. You see it says LOG. And then type in your 10 plus 1, close your parenthesis, and enter. And so we got 79.8199, so let's just say 79.8%. Okay, and this is just showing you that it's going to follow the same rules and everything that when we had an actual base written, okay? The only difference is they just didn't write the base that time. Common logs, base 10. Then we have natural logarithms. This is a logarithmic function with a base of e is called a natural log function. The function f of x equals log base e of x is usually expressed as f of x equals ln of x. So if you see ln of x, you know that's the same thing as log base e of x. Okay, and so a lot of times when I see an ln of x, I'll just go ahead and put a little e there to remind me my base is e. And so we can do this the same as what we did in the other stuff. So if I have the natural log of x equals 4, then I know my base, because it's natural log, I have a base of e. My x is x, and my y is 4. So I can do my b to the y equals x. And remember, e is an irrational number. It's like pi, so you're just going to get a number that goes on forever, so you can leave it like that. You could also have like the natural log of e to the 5th equals y. Now notice that e is the same size as like that n. That is not your e, that's a base, okay? So you've got another little subscript e down there that they didn't have to write because they put ln. So your base is e, your x would be that e to the 5th, and your y is your y. So b to the y equals your x. Base is the same, so we know that y is equal to 5. Follows the same properties as all the others. And then here's an example here. So it says when the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function, given there, models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. Alright, so they gave us an equation here. So what does f of x represent? Well, it says f of x is in degrees Fahrenheit, so I need to go backwards. It's the temperature increase. And what does x represent? Well, it says x minutes, so it's our number of minutes. Alright, so let's see what we're after. It says use the function to find the temperature increase, so we're looking for the temperature increase, to the nearest degree, so we're going to round to a whole number, after 30 minutes. So that means our x is 30. So we got 13.4 natural log. It's going to open a parenthesis. You're going to type in that 30. That minus 11.6 is not in parentheses with it, so close it and type in minus 11.6. So 13.4 natural log is right next to the 4 button on your calculator of 30. Close that parenthesis, minus 11.6. And so I got 33.976 said to the nearest degree, so that's 34 degrees Fahrenheit.